Hello everyone, my name is John. In this video, I'll be showcasing my own recreation of God of War's Leviathan axe throw, developed in Unreal Engine 5 with C++. This gameplay mechanic is a key part of combat in God of War, allowing Kratos to throw and recall his Leviathan axe with precision and apply damage effects to his enemies. This gameplay mechanic is a prime example of why Sony Santa Monica is one of the best in the industry. I was fascinated by how this was made, so I set out to recreate it as accurately as possible, exercising the gameplay engineering aspect of game development. Before we go over how I developed this, here's a short demo of the project. Enjoy! Before we begin talking about the Leviathan axe, let's briefly talk about how the character was made. To start, I found this character model on the Fab Marketplace provided by Bergamov Maxim in their Fantasy Characters asset pack. He fairly resembles Kratos from God of War. I created a custom character class for the player called Hero Character. I also implemented my own locomotion system for the character with a custom anim instance that will drive the character's animations. Now let's get to the most important part of this project, the Leviathan axe. For the static mesh, I used this ancient warrior axe provided by Ulusanar on the Fab Marketplace. I created an actor-derived class called Leviathan axe that has useful properties, such as the static mesh, as well as crucial functions for the axe throw. I'll get back to how this code works in a moment. There are two types of throws. There's the light throw, which happens when the player aims and presses the light attack button, and there's the heavy throw, which happens when the player aims and presses the heavy attack button. You need to detach the axe from the character's hand and find the launch rotation. The launch rotation should match its aim rotation. However, with the light throw, there needs to be a bit of an offset to its roll. At the start of a light throw, the axe's roll is at what looks to be a 75-degree offset. In this case, we need to add an offset to its initial rotation. Heavy throws won't have this offset. Now we need to find the launch point. The axe should launch at the right side of the character, but straight across from the player's crosshair, so the player can have precise throws. This will be our target launch point. Now, how do we get the launch point location? We need to get the location and direction of the crosshair in world space. I created a function that retrieves the location of the crosshair texture in screen space, allowing the crosshair texture to be placed anywhere on the screen. Once we have the screen space location of the crosshair, we need to call the deproject screen to world function to get the location and direction in world space. Okay, great. With the information we've gathered, we need to do some linear algebra to find the launch point. What we need to do is get the vector from the crosshair to the axe's initial location. Now we project that vector onto the crosshair direction vector, then multiply that value with the crosshair direction vector. Now we add that vector to the crosshair's location. We finally have the launch point for the axe. Now our goal is to launch the axe. First we need to find the launch velocity. The direction of this velocity is going to be the crosshair direction. The magnitude of this velocity is going to depend on if the player is doing a light or heavy throw. The speed of the light throw should be faster than the heavy throw. Now we're going to pass the velocity as an argument into the Leviathan axe's launch function. Let's take a look at how the launch function works. I attached a rotating movement component to the axe when it spins in the air. We're going to activate that component. Now we're going to store the current location of the axe. This will help with collision detection later on. I also attached a projectile movement component. It will be responsible for launching the axe. We're going to set its velocity, and before we activate it, we're going to set its gravity skill to 0. In God of War, gravity doesn't take effect initially. Gravity is applied once it has moved past a certain distance. We'll apply gravity later on. Now let's handle gravity. Gravity should be applied once it has passed a certain distance. Every frame in the tick function, we're going to check the distance squared between the launch point and its current location. If it has passed the distance squared required to apply gravity, then gravity will be triggered. Now let's go over collision. A line trace is created starting from the axe's location in the previous frame to the axe's current location. If the line trace gets a hit, it's time to handle collision. We're going to deactivate both the rotating and projectile movement components. Now we need to set a new orientation for the axe. The axe's yaw and roll should remain the same, but the pitch needs to be influenced by the surface it has collided with. To define a new orientation, we need the object's x, y, and z basis vectors, also known as the forward, right, and up vectors. The axe's y vector should remain the same. To get the z vector, we need to perform a cross product between the negated impact normal and the y vector. 2 basis vectors is all we need to create a new f rotator, which will represent the axe's new rotation. We also need to add a bit of randomness to the axe's pitch. A random offset between -45 and 3 degrees will work. Now we need to set the final location. I created a socket on the axe's static mesh called impact socket. The location of this socket helps determine how deep the axe should cut into a hit surface. So if you want a deep cut, place the socket deeper into the mesh. With the axe's impact socket location and the impact point, we can now find the axe's final location. Finally, we're going to attach the axe to the object it hit. And there we have it. Now let's talk about the axe recall. I created a function for the axe called fly to target. This function is responsible for initiating the axe to fly to a target location, as well as set a target rotation that the axe should have by the end of its flight. In this case, the target location and rotation should be of the character's right hand for the axe recall. Let's take a look at how this function works. We need to set the properties for a member variable called m_flightinfo. The data type for this variable is called flightinfo, which is a private nested struct I defined that encapsulates all the data related to the axe's flight. We need to set the target location, the target rotation, and m_b interpreting target rotation to false. In God of War, when the axe gets recalled, it spins for most of the duration, but once it gets close to Kratos, it starts rotating to the orientation of Kratos' hand. We need to set this to false because it doesn't interpolate to the target rotation initially. Now we need to calculate the duration of the flight. The axe recall should last for at most 1 second. We're then going to calculate the radius of the curved path that the axe is going to follow. When the axe is recalled, it's going to follow a curved path to the character's hand. We're going to set its current rotation to its target rotation, but with an offset of 135 degrees. Now we're going to set a timer that's going to last for the duration of the flight. This timer is going to be important for moving the axe. That's all for the setup of the axe flight. Now let's talk about what needs to be done every frame to move and rotate the axe. Let's start with movement. In order to move the axe to its target location, we're going to perform a linear interpolation between the initial and target location every frame. We're going to use the flight timer to query how much time has passed and use that value to calculate an alpha value for the lerp function. The result of this linear interpolation will be the new location for the axe. However, we still need to curve the path that the axe moves along. I use this equation to calculate the offset needed to curve the path. Here's what it looks like. Now we need to handle rotation. The axe spins for most of the flight, but once it gets close to the character's hand, it will start rotating to the orientation of the character's hand. We need to activate the rotating movement component to get the axe to start spinning. And then every frame, we need to check if the axe is within a close distance to its target location. If it is, it should start interpolating to the target rotation. This is similar to how we interpolated the axe's location to the target location, but instead, we're going to perform a spherical linear interpolation to smoothly rotate the axe to its target rotation. I want to mention that the reason that we use timers is to move and rotate the axe within a certain time frame, and also to calculate the alpha value we need for interpolation functions. And there we have it, the axe throw and recall. Now, let's talk about artificial intelligence. I originally wasn't going to include AI in this project, but I figured it will help showcase the Leviathan axe's capabilities. For the AI character, I used this character model provided on the Mixamo website. I created a character class called Enemy Character that is controlled by an AI controller, as well as a behavior tree. In God of War, when the player does a light throw at an enemy, the Leviathan axe bounces off the enemy as the enemy gets knocked back. Let's go over implementing this light throw attack before we go over the heavy throw attack. I created this nested enum in the Leviathan axe class called eHit type request. This describes what the axe needs to do once it hits an enemy. This is a request because it might be rejected if it hits an enemy that is already dead. This request gets passed in the axe's launch function. When the player does a light throw, it uses the EHT_knockback enumerator because the enemy should be knocked back. When the axe collides with an object, it first checks if the object it hit implements an interface called iAxe damageable interface. If it does, that means the axe hit an enemy because the enemy character class inherits from that interface. Now the axe is going to call a function called ricochet off hit object. The argument we need to pass into the function should be the velocity right before collision. What this function does is redirect the velocity of the axe so it ricochets off the hit enemy. We're going to rotate the velocity upwards so it looks like it bounces off the enemy in the upwards direction. We're also going to shrink the velocity significantly. We're then going to call the launch function, passing in the new velocity and the previous hit type request, which is EHT_knockback. And finally, we're going to increase the gravity scale so it falls quicker than it did before. A function in the enemy character class called getKnockedBack will be called, which plays a specific section of an animation montage depending on the direction the axe hit the enemy. Here's the result for light throws. Now let's go over heavy throws. When the player does a heavy throw at an enemy, the axe attaches to the enemy and freezes them for a limited time. When the axe collides with an enemy character, we need to first attach it to the enemy character's mesh. But the difficult part here is deciding where exactly on the enemy character's mesh we're going to attach the axe to. For this reason, I placed several sockets on the enemy character's mesh, which are good locations that the axe can attach to. I created a function that extracts all of the socket locations from the mesh and chooses the socket that is closest to the axe. The axe is then going to attach to that chosen socket. Here's how it looks. Now, to freeze the enemy, we're going to gradually change the color of the enemy's texture to a white snow type of color by activating this custom material function. We're then going to set a timer that is a short delay before actually freezing the enemy. Once this delay is complete, we're going to pause the enemy's current animation. We're then going to set another timer which lasts for the duration of how long the enemy should be frozen for. Once that timer is complete, the enemy is going to unfreeze itself, resuming the animation and restoring the original color of the mesh's texture. The unfreeze function is also called when the axe is recalled. Also, when the enemy is unfrozen after the freeze timer is completed, the axe will be notified and then will detach and drop from the enemy. Now let's talk about axe pinning. In God of War, the player has the ability to pin an enemy against a wall by performing a heavy throw in the direction of the wall that the enemy is in front of. I created an actor-derived class called Pinnable Wall, which will contain a static mesh that the Leviathan axe can pin an enemy against. When the Leviathan axe hits an enemy, it's going to perform a line trace starting from the axe's location and in the direction of its velocity. The length of this line trace is going to be the size of this float member variable called m_pinnable wall search distance. This distance is essentially the distance between the enemy and a pinnable wall that is required to allow the axe to pin the enemy. If the line trace gets a hit and the hit actor is a pinnable wall, then the axe is going to pin the enemy against it. Now, how do we pin the enemy? First, we need to store a pointer to the enemy, then redirect the axe's current velocity so the enemy stays above ground when the axe is carrying the enemy. One thing I want to mention here is this is where I actually add my own little twist to it. In God of War, the axe doesn't carry the enemy, it sort of just pushes the enemy against the wall. I thought it would be really cool if the axe is able to carry the enemy in the air as it moves towards the wall. Now we're going to modify some properties to ensure that gravity isn't going to be applied to the axe. When the axe carries an enemy, it should launch straight into the direction of the wall without gravity ever being a factor. Now we're going to do some alignment to the axe and the enemy's orientation. We're going to align the axe's orientation so it's influenced by the enemy's impact normal, attach the enemy to the axe, and align the enemy's orientation so it's facing the axe. Then we're going to move the enemy into the axe's impact socket location so it looks like the axe cut into the enemy's mesh. Now we've completed the logic for carrying the enemy. What do we do when the axe hits the wall? We need to rotate the enemy so it aligns with the wall's normal vector. This way the enemy looks like it's pinned flat against the wall. We also need to move the enemy in the opposite direction of the wall so the enemy's mesh is inside of the wall. Now we're done with pinning the enemy. All we need to do now is release the enemy when the axe gets recalled. We do this by applying ragdoll physics to the enemy's mesh, which separates it from its root component. And there we have it, everyone. God of War's Leviathan axe throw recreated in Unreal Engine 5 with C++. I wanted this video to be a short overview of the entire project, only covering the main points. I left out some details, so I left a link to a GitHub repository in the description so you can look at the source code to better understand how it works. There is also a link in the description where you can download and play the demo. Credits for all of the assets used in this project are in the description. This includes the links to all of the 3D models, animations, and so on. Thanks for watching, everyone. Please leave a comment if you have any questions.